Hi everybody, it's Miss Peachy from your WCA physics class, and today I'm going to be doing a supplemental tutorial on the universal law of gravitation. So again, I want to remind you of the difference between a law and a theory. If you remember, a law is going to be describing a physical phenomenon in nature. So most of the time a law is a mathematical description. Going to tell us, what we can expect. It makes accurate predictions, but it doesn't tell us why things occur the way they do. So the law of gravity is oftentimes cited as kind of like the prime example of what a law is. Law of gravity is Isaac Newton's description of the force of gravity and how it behaves. And the force of gravity depends upon the mass of the objects and the distance between those two objects. And so his mathematical description is one that's going to show us the relationship between mass and distance and gravitational force. When it comes to why is gravity, well, why do we have gravity? That actually came quite a bit later with Albert Einstein. So Einstein came up with his theory of relativity, which explained why we have gravity, among other things. Okay, so explained why we have gravity, and again, that's a theory because it's an explanation of something, and even though it's not a description of gravity, you can't use the theory of relativity to mathematically quantify gravity, but it explains why gravity exists, and that it is, when a theory is given the status of a theory, then we know that we can make predictions that can come true based upon the theory itself, and evidence that has been collected supports that theory. Okay, so just kind of reminding you the difference between a theory and a law here. So I'm going to look at the universal law of gravitation, and I'm going to go ahead and turn my camera down to my notebook again. Flip it around. Go on full screen for you for a sec. All right, so you can see my physics notebook here. And the universal law of gravitation is one of the many inverse square laws that are found in physics, which is kind of cool actually that you think about it, that the same kind of format we see for a number of different things. Inverse square. Let's look at the law itself and then explain what that actually means to you. Okay, so the formula for the universal law of gravitation says that the force of gravity is equal to the gravitational constant times the mass of the first object times the mass of the second object divided by a square of the distances. Now, to figure out how did we get G, the universal gravitational constant, I would refer you to your textbook on page 245. Or there are several YouTube videos that do a great job of explaining how the value of G was determined. This is a constant, remember, just like our spring constants are dependent upon like the stiffness of the springs and things like that. The universal gravitational constant is dependent upon the innate force of gravity itself. So again, look under Henry Cavendish's experiment and how he was able to derive the value for G. But we're not going to be able to have time to go through that today, okay? I will tell you that the universal gravitational constant, large G, has a value of 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. So that is the value of g, okay? That's what we're always going to be using for g. Now, the whole idea behind an inverse square law is that whatever it is that we're looking at is going to be decreasing by the square of the distance. In other words, if we increase the distance, the value of that object, or that value of whatever it is going to decrease by a square of that distance. Light is another phenomenon that follows the inverse square law. So when we're looking at light, it's luminosity. It's how bright something is. The brightness decreases by a square of the distance. When we're looking at gravity, it's force. It's the force of gravity, which is decreasing by a square of its distance. So it's not necessarily a standard thing, but whatever it is we're measuring is decreasing by a square of the distance. So what that means is that if I have the Earth here, and I have the moon here, if I were to take the moon and double the distance, put the moon twice as far away from the Earth, I'm doubling the distance. So d becomes 2d instead of d. Because it's now 2d, I'm squaring that. So this would make gravity 4 times less. Okay? So you always got to remember that however much you increase or decrease distance, you kind of pencil in as a little phantom number in front here, and then you have to square it, and that's going to tell us how much that's going to affect gravity. On the other hand, mass has a directly proportional relationship. If I take the moon, leave it at the same distance, and I double its mass, I double the mass of the moon, and the moon, we'll call the moon M2 here. If I'm doubling the mass, I'm penciling a phantom 2 in front is there. That's going to double the force of gravity. So doubling the mass is going to cause gravity to increase by a factor of 2 as well. If I doubled the mass of the Earth and doubled the mass of the moon, that means gravity goes up by a factor of 4 because I'm doing both of them by 2. Okay? So again, this is a law. It's a mathematical description of how gravity behaves, how the force of gravity can be quantified between two objects, because when we're looking at force, remember Newton's third law. For every action, there is an equal and opposite reaction. You have to discuss forces in pairs or they don't make sense. So we need to look at two objects and the force between them. That's why we have an M1 and an M2. So force of gravity is G, M1, M2 divided by the square of the distance. And that kind of got a little fuzzy there for a second, but it looks like it is focusing. There we go. The other thing to take into consideration here, too, is that these objects can be any two objects. This could be the Earth and the Moon. It's a very poorly drawn size comparison there, but that can be the Earth and the Moon. It can be the Earth and the Sun. It could be you on the Earth. And then we would take the mass of you and the mass of the Earth and the distance between the center of mass of both objects. Okay? So there's gravity whenever you have any two objects that are made of mass. There's going to be a gravitational force between them. Just, there's this gravitational force is a field force. It's a field force. So that also means that every object around you is going to have its own gravitational field force. And you're going to be attracted to the one that has the largest. So if the Earth, we're standing on the Earth, that's going to have the greatest effect on us because it has the greatest magnitude. Okay. I think that does a pretty good explanation of the universal law of gravitation. If you have any additional questions or concerns, feel free to contact me at extension 2204, or you can send me a webmail message. Ta-da! Have a great day, everybody.